Greetings. A very common question is that why do we assume ideal turbines to be adiabatic? Later on, in the second law, we see that an ideal turbine is both adiabatic and reversible. Well, second law justifies the ideal turbine to be reversible and explains why. But why adiabatic? Today, I solve an example just to show what a difference an adiabatic turbine makes. The question that I want to solve is if you have a turbine, which we usually draw like this and call it a turbine, and then place a shaft that has work out of it. There is usually an inlet to the turbine, and there is also an exit to the turbine. So the numbers I have taken from one of my references, the book by Terms, which is a very good book, but I usually extend the problem to solve other things that are not even requested from the original problem. So the inlet temperature, T equals 400 degrees C. That's the inlet temperature, and the inlet pressure is 0.4 megapascals. That's the inlet temperature and the inlet pressure. Now, we are also given the outlet temperature and pressure. T equals 200 degrees C and P equals 0.1013 megapascal, which is an atmosphere. Okay, now the question is if we ignore all velocity and elevation effects, so there's no change in velocity, or at least that is ignorable. So delta V, we assume equal 0, delta Z equal 0. Also, initially, we assume that the turbine is adiabatic. That means there is no heat transfer from the turbine. Now, the question is how much work do we get from such a turbine? The method to solve these problems is very usual, as we have always done. So what we do is first we decide on the control volume, decide on the control volume. 2, calculate properties, calculate or read from a table the properties. 3, simplify conservation equations for the problem at hand. Simplify conservation equations for the problem at hand. 4, draw a diagram. And finally, collect everything towards the final answer. Collect everything towards a final answer. And this is the pattern we usually follow. And as a first step, what I do is to decide on the control volume, which is the turbine. Of course, what we are assuming is that the material doesn't, there is no change in the material, and we don't take it really into account, and we assume that it doesn't change. So it is not important in this case if you assume control volume to be the air inside the turbine or the material itself, because it will be a steady state problem and there will be no change in the conditions inside control volume. So it would not make a difference if you take the material of the control of the turbine inside the control volume or not. So these are what we have. Now, uh, decided on the control volume. Now we simplify our conservation equations. You don't need to do these things in order, or you don't need to do them completely. You might do them alternatively, do one and a half and then complete it later on. Depends on the problem how you do it, but these are the steps you have to take. So the mass conservation equation tells us that the change of mass inside the controlled volume is a function of the mass entering minus the mass leaving the controlled volume. And since this is a steady state problem, it means that the turbine does not change and the problem continues. We have no start, initial point, or an end point. So the problem is continuous. Therefore, this term vanishes and we have the m dot I equals m dot E. And that equals A, which is AV over V, which is the area, velocity, and specific volume. This could be for the inlet or the exit. That's no problem. And that equals, you could replace V from the perfect gas, and that would make P A V divided by R T. This is valid. This equation is valid either for the inlet channel or for the exit channel. That's both equal. We just have to add indices to this equation. Now, the first law of thermodynamics tells us that dE CV by dt equals m dot I times hi plus vi squared over 2 plus jzi minus m dot e times he plus ve squared over 2 plus jze plus q dot and minus w dot. Now, for this equation, the problem is steady state, so this term vanishes. There are no changes in velocity, no changes in elevation, and the problem, as still as it is initially is adiabatic. So that term also vanishes. So the final look of the problem would be 0 equals m dot I hi minus m dot e he and minus w dot. And if we divide everything by m dot, that would make 0 equals hi minus he and minus w, which has dimensions kilojoules per kilograms. This equation has dimensions kilojoules, and this equation has dimensions kilojoules per kilograms. Now, we may also, for a perfect gas, if we assume Cp0 to be constant, write this as 0 equals Cp0 times Ti minus Te and minus W, where we have everything except W. We may read Cp0 for air from perfect gas tables, and that is 1.0045 kilojoules per kilograms Kelvin. And if we replace everything in this equation, the outcome would be 0 equals 1.0045 times. Please note that this 400 is 400 degrees C, and we shall always use absolute values in our equations. Sometimes they cancel out, but we should remember that the, the true practice, the correct practice, is always to use absolute values. So it is 400 plus 273.15 minus 200 plus 273.15 and minus W. And the answer for W would be 200.009 kilojoules per kilograms. That's the answer for W. And we may also use this equation to calculate a sort of ratio between inlet and exit. If we write this equation both for inlet and for exit, it will look like this: Pi times Ai times Vi divided by Rti equals Pe times Ae times Ve divided by Rt. We have assumed that the changes in velocity are negligible. R is also the gas constant for air, which is also the same, doesn't change, and therefore the conclusion is that A E divided by AI would be Pi times TE divided by Pe times Ti, where we do have all the values, and therefore we can calculate, write down 0.4 times 473.15 divided by 0.10135 times 673.15, and the answer would be 2.777 2.741. That means that the turbine has expanded. Air, the air has expanded inside the turbine, and therefore it needs a larger area at the exit. This is why we draw a turbine schematic of a turbine like this. The exit area should be larger than the inlet area. But this was the initial problem, which wasn't that hard to solve. Now, the question is this. We are changing the problem now, and I write it in a different color. Uh, and the question is this. If we had some heat transfer, so now we are changing the question and we say if we had some heat transfer, what would have happened? I mean, if usually turbines are very well insulated, steam turbines usually have a large dome over them with lots of packings and lots of insulation so that the heat transfer would be basically zero. Now, if that insulation is torn, if that insulation is gone, then you might as well have as much heat transfer as you have work. So you would well end up Q equals W. If there was as much heat transfer as there much work, of course, note this is the absolute values because you might argue that the sign convention should be followed, which is true. So if the absolute value is right, it means that if we lose as much energy through work as we lose through heat, and they are the same, then what would happen? Then here Q would not be zero, but Q would equal work, and therefore if we have calculated work to be 200, Q would also be 200.009. That would change this equation. And here we would have W plus Q. Note that I am writing the second part of the question in red. And therefore, what we would have here is that we no longer would have exit temperature would no longer be 200 degrees centigrade, and I will write it here. The exit temperature would no longer be 200 degrees C. What it would be, if you want to calculate that, it's straightforward. 0 equals 1.0045 times 673.15 minus TE, which is now we need the exit temperature, and that would equal, here you see here, it was minus 200, and now it will be minus 400. 0 minus 400.018 kilojoules per kilogram, because we have both lost work and we have lost heat. And the outcome would mean that TE would equal 274.9 kelvins. which is far less than what we had here. Here we had 473. That was the temperature of air going out of the turbine. And now we have lost it. So the temperature is 274.9. So the exit temperature is cooler and can do less work in future stages. Later on, in the chapter on availability, we would see that when temperature is low, the air is less available, it can do less work in the later stages. If we wanted to have the same exit temperature, then the work would be halved. I mean, we only would get 100 kilojoules per kilograms of work. So I would write this down here, that if it was required to have the same exit temperature, then this 200 kilojoules per kilogram that was the work obtained would be halved, and half of it would be work, and half of it would be work, and half of it would be heat transfer. Then work would only be 100 kilojoules per kilograms. So we would only get half the work we require. Now we have done all we wanted, except we have not drawn things on a diagram, and it's very important to draw the problem on a diagram. So how we do it? Let's draw a diagram. Our diagram is a TV diagram, which is this one. This is TV diagram, and the constant pressure lines would look like this. This is P equals 0.10135 megapascals, and this is P equals 0.4 megapascals. So this is our diagram. Now, just to have an idea of how should draw this, we should have some values for V. And it's not difficult because we have two properties of inlet and exit. So we can have V for both inlet and exit. V1 equals R T1 over P1. This is the equation of the state for perfect gas, and that equals 0.287 times 673.15 divided by 400, and therefore V1 in cubic meters per kilograms would be 0.483 cubic meters per kilograms. That's the dimension. we could also calculate V2. V2 equals 0.287, which is the gas constant for air, times 473.15 and divided by 101.35. You see, this is kilopascals, this is megapascals, and this is kilojoules per kilogram. So our dimensions match. V2 would be 1.34 cubic meters per kilogram. So if you want to draw a good drawing for these two values, in fact, one should be somewhere here. This is 0.1 and 0.2 should be somewhere here where V1 is 0.483. I would write dimension for V, and this is here V2. This is 0.2, and V is 1.34. Fortunately, in this problem, we managed to draw somehow up to scale. T1 is 400 degrees C, but we should do it in kelvins, which is 670.15. And for 2, it is 200 or 473.15. This is T1 and T2. Okay, so this was the process. This was the initial and the final point, and the process between 1 and 2 would look like this one. This is the process between 1 and 2. But we had another condition where we had also heat transfer. If that had happened, V2 would be equal, for the case with heat transfer, for the case with heat transfer, V2 would equal 0.287 times 274.9. I mean, if the initial and final points had remained the same, then that was the case. Only work had changed. But if they had changed, then it is 101.35, and that would equal 0.778 cubic meters per kilograms. And that is somewhere like here. So let's call it 2, the red number 2, and the process would go here. This is the process that would have happened if there was as much heat transfer from the turbine as the work collected from it. So we see why it is good to have an adiabatic turbine. Simply, an adiabatic turbine would produce more work for the same inlet or exit conditions. Okay, thank you very much for watching. Cheers.